All right, so what you need to do is on the paper, you need to record. It's going to be upside down. You just record on here the conclusions that we make together. And that's what will get you your done stamp. First of all, I had you hold the ruler off the table at the 10-inch mark, and I had you flick it either like this or like that. And then you moved it to 7. Do you hear a difference in the sound? Then we went to 4. Okay. The way you perceive the highness or the lowness of the sound is the pitch. Is this a higher pitch or a lower pitch? Right. Is that higher or is that higher? This was the higher pitch sound. Hear that? That's the pitch, the highness or the lowness of the sound. I'll even go, that is a lower pitch sound, correct? Okay, so the conclusion that we wanted to make here is, how does the length of the wave affect the pitch? Because basically, in this case here, you were making a wave over 2 inches, correct? You were giving some energy, you were making this ruler come down, you were releasing it, and it was waving back and forth over a 2-inch distance. And you made it over a 7-inch distance. And you made it over a 9-inch distance. So does the length of the wave affect the pitch? Yes. Okay. Now we typically don't relate wavelength to pitch. What's the term that is related to pitch? It is frequency. But are wavelength and frequency related? Okay. So we were making the wavelength bigger, correct? So what was happening to the pitch? It was going lower, right? It would be a lower pitch. So the shorter ruler had the shortest wavelength, which would have been the highest frequency and the higher pitch. So the conclusion we were getting here is that the length of the thing that is vibrating, or the wavelength, affects the frequency, which affects the pitch. All right, let me say that one more time. The different materials vibrate differently. And if you're vibrating differently, you're going to have a different frequency, hence a different pitch and a different sound. We know that metal doesn't wiggle the same way as plastic, and it doesn't wiggle the same way as wood. So you get a different frequency, hence a different sound. Okay, so for part A number 3, it's the same material. It was both wood, and you were having the same length, so the wavelength was the same. Was number 3 for part A the same sound? Not. Okay, so it seems like there's another variable here that affects the sound that you get, and that is the amount of material or the size of the material. The one ruler, the thicker ruler, is going to vibrate differently than the thinner ruler. Do you remember which one vibrated at a higher frequency? Which one's easier to wiggle back and forth more? The thinner one. Correct. Because a thinner one is going to wiggle. You don't have as much mass to wiggle back and forth. So the period and the frequency are going to be different than if you're trying to wiggle something that is a lot more stuff to get it moving. Do you recognize this formula that dictated the motion of something that was wiggling back and forth on a spring? Right? Okay. Did the mass make a difference? It did. So think about that with the rulers. The thicker, heavier, more massive ruler is going to have a different wiggling or a different motion, a different period, and hence a different frequency than the thinner one. All right, so for part B, we're looking at different rubber bands, and you pluck the rubber bands and they vibrated back and forth, and that vibration back and forth compresses and unstretches or causes rarefactions in the air, and that energy is transmitted to our ear and we hear a sound. Okay, so you had it just where it was beginning to be stretched, and I had you say pluck the rubber band and make a sound, and then pull the rubber band tighter and repeat the procedure. Did the sound in the rubber band change when you pulled it tighter? Yeah. It did. Same rubber band, same material, same mass. All right, all that was the same. So what was changing about the rubber band? The rubber band elasticity. It's the same stretchy rubber band. We got to go back to fall semester. The tension. Thank you. We changed the tension in the rubber band. Did it change how the rubber band oscillated back and forth? It did. Okay. So how did it change it? What's the relationship? As you made it tighter, what happened to the frequency? But the sound. The pitch then, sorry. Made the higher. The higher the tension, the higher the pitch. That's the conclusion I want you to make about part B, number 1. The higher the tension, the higher the pitch. Okay, thicker and then the thinner. Did you notice the difference between the thick and the thin? Which one vibrated more frequently? The thinner one. And it's the same thing as with the ruler. You get more mass, it's harder to get it wiggling back and forth. It wiggles back and forth a little bit slower, so it has a lower frequency, so a lower pitch. So the conclusion we want for part B, number 2 is the thicker the string. We'll go ahead and start saying strings at this point because we're going to relate this to stringed instruments like a guitar, violin. The thicker the string, the lower the pitch, which means the lower the frequency because it's harder to get it to move back and forth when it's a big heavy string. So in part B, you took the same rubber band and you stretched it a certain length. And then I said, just pull it up farther. What wave term is that referring to? When you displace it farther from equilibrium? Speak up, Tina. Amplitude. If I have my rubber band like this is the amplitude, correct? With a wave or a sound, what does the amplitude mean? Or what does it affect about the sound? The amount of energy or the loudness of it. It doesn't change the period or the frequency, does it? So when you took the same rubber band and you just displaced it further, you got exactly the same sound. However, the sound was what? Was it more or less loud? It should have been louder. So that when you displace it more, you get a louder sound because it's pushing more air. And your ears perceive that as a louder sound. Your ears are going to receive more energy because the more the rubber band is stretched, the more air it's going to push. Meaning the more air hits your eardrum and the louder the sound. All right, for part C, number 1, I had you put the ruler on the bottom of the string and I had you hit it up against the table and you were listening to the sound. You could hear the sound. You heard the sound very differently than if you just heard it through the air. Think about how sound is transmitted. It's energy that is transmitted through matter. When I took a metal ruler and I just hit it through the air, just vibrate it like this. Let's take the string. Oh, I got this one here. When I do this, you hear the sound getting to your ears through what? Air is the medium. When I had you take the string and put the string in your ear, you are now hearing the energy transmitted how? And through the air still, because you don't totally block off your ear, do you? So you're hearing the sound come to you through two different mediums. Does sound travel the same through a string as it does through the air? Did you hear the ruler sound differently when you put the string in your ear? Yes. Okay, there were two things you should have noticed about that. One was the pitch different. That's pretty high, isn't it? But when you put it with the string in your ears, it almost sounded like a big old church bell, didn't it? Because the string is vibrating differently than the air. You also should have perceived that it's louder. Because the string basically channels the energy straight into your ear. When you get energy like this, it's all going out all three dimensions through the ear at one time, and it spreads out until it gets to your ear. By putting the string in your ear, you're basically giving all of that energy, all that vibrating energy, a direct path straight to your ear. So for part C, number 1, you should have heard the sound louder, and you should have heard a different pitch because the medium is different. And all mediums transmit their energy differently. Now, in part C, number 2, the only thing I had you do was shorten the string. Was there a difference in the sound between part 1 and part 2? It was louder, but it sounded the same, didn't it? Okay. The pitch didn't change because it's still the same stuff vibrating. Why was it louder? You lost less energy because there was the source was closer to your ears. It wasn't spread out as much. Now this is where we had a problem. And I actually had to go get some confirmation from this from some younger ears in the department. Let's talk a theoretical sense here. Should the ruler sound the same through the wire as through the string? It should not, right? Because they are two different mediums transmitting the sound. Did you perceive a difference in the pitch of the sound with the wire and the string? It was higher? Okay. All right. Your ears are much better than mine. Like I don't trust myself. To me, I could not hear enough of a distinct difference in the pitch between the wire and the string. But I've got old guy ears, and it's very well documented how bad my hearing is. One thing I could perceive, though, I notice when I use the wire, I notice a lot of reverberation. What does reverberation mean? It means sound that goes out and then comes back to you. When you used it, when you were swinging on the string, and it makes a sound, the ruler's vibrating, and it sends energy through the string, and it gets to your ear. Does any energy come back? Yes. And if it gets back to here, it'll go back and forth along the string, correct? Okay. The string, because it's not very dense, it loses a lot of energy. There's a lot of air in there, and it loses the energy to the air around it very quickly. But metals transmit energy very easily, don't they? So when you use the metal, the metals transmitted the sound so easily that when you hit it against the table, the energy went up, some of it went into your ear, but then a lot of it came right back down, didn't it? Got to here and then did what? Came back up. So I actually heard the same vibrations more than once because I'm using a wire instead of string. And it had more like a gonging sound. I could perceive that myself. I don't know if you could or not. But yes, it sounded like almost like a warbling sound because I was hearing multiple vibrations from the same source at once. Part D.
Now for part 1, for part C 1 to 2, like part 2 was shorter than part 1, the length of the string.
Yes.
If the length of the string was shorter, why was it higher?
Because what was the vibrating object? It was still the ruler, right?
But wasn't the vibration passing through the string as well?
Yeah, but that was the difference in the medium. You didn't have the string tight enough to make that a difference. All right, with the tuning forks, you struck the tuning fork. Did you notice the difference between the different tuning forks? Long ones versus short ones, correct? Okay. Did you notice a pattern?
Yeah, the higher up the louder.
The louder? What about the pitch?
I mean, the higher pitch.
The longer ones had a lower pitch, and the shorter ones had a higher pitch. Because the shorter ones can't wiggle as far, can they? So they got to wiggle more quickly, and they produced more frequency and a higher pitch. The longer ones could wiggle back and forth more, which means it takes them longer to wiggle back and forth, which means a lower frequency and hence a lower pitch. We'll try it, right? Because you got time to we'll prove. Right. What's that? The longer tuning forks produced a lower frequency. With this right here, when you took two different tuning forks, and you listened to one and then put the other one up and you took one away, when you had two tuning forks at your ear, you should have not heard a very clear sound or as clear a sound. When you have two sound makers at your ear, they're both making waves. Two different waves, what do they do to each other? They either cancel each other out or they do what? They add together. Either way, they're getting in each other's way, aren't they? So you're hearing two sounds kind of warbled together, combining, and you didn't hear a very clear sound. If you took one of the tuning forks away and you only heard one of the sound, it became a lot more clear because you got rid of the wave that was interfering with that sound. This was a good example about how wave interference makes sound not very clear. Now part D was kind of some fun here. What was I trying to show you with part D? What did I want you to see? What did the paperclip do? It went back and forth like crazy, didn't it? What was pushing the paperclip? What was the actual physical stuff? Air. This was meant to show you, because you can't see the air going back and forth, can you? But when you put the paperclip in the middle, you saw the paperclip going back and forth, back and forth, back and forth. You can't even see the ends of a tuning fork moving back and forth that easily. But when you put the paperclip in there, you could actually see the effect of the air pushing back and forth because the paperclip wiggled. The whole point to this was to show you that's how sound is created. It's air being pushed back and forth. On a note, why do you think I told you to only strike the tuning forks on something soft? What's that? To not bend the metal. Because what happens if I bend the metal? It's going to change the sound, isn't it? It's going to change how it vibrates, and that would change the frequency. Each one of these tuning forks has a set frequency. You can actually use them to tune musical instruments because they are made very precisely to give you one specific frequency. And if we start banging them on different stuff and we take little nicks of metal out and we change the shape, it will not provide that frequency. Part D, number 4, yes. What did I want you to see here? Water was vibrating back and forth, right? Did you see the little circular waves coming out from where you put the tuning fork in? They're not very big, but did you see a high point and a low point? Yes. To see the wave, right? To see the waveform, you basically got a crest and a trough, correct? Once again, this was meant to show you that sound is producing real waves, where it has a squeezed together part and a stretched out part. And you saw that in the water because you saw a physical piling up of the water where it was squeezed together. And then you saw it where it had a trough where the water stretched out. And that's how sound works. Okay, so I get the tuning fork vibrating. Can you guys all hear that? Really, you're better than me. All right. It's not very loud though, is it? This tuning fork's kind of small, only vibrates a very small piece of air, doesn't it? But if I can take it, that's not the best tune. Does that sound louder? Remember, sound is vibrating air. This is an example of forced vibrations. The paper is not vibrating, the tuning fork is. When I put the tuning fork up against the paper, does it push the air on this side of the paper? You heard the paper vibrating, correct? It was forced to vibrate at however the tuning fork was vibrating, which then forced the air on this side of the paper to vibrate. Look at these two objects. Which one can push more air? This. This is an example of forced vibrations, and this is one of the primary tenets of making musical noise, is to try to make something vibrate that's going to vibrate more air. All right. The different type of paper. In theory, the different types of paper should vibrate differently and give you a different sound. I think the papers I had were too similar in size and density that we didn't get something, we didn't get enough vibration that we could perceive it. But if you think a woodwind instrument, something that has a reed to it, clarinet, what else has a reed to it? Yeah, not the same time. You get the different material vibrating and you're going to get a different sound. Now, the tube. When you struck the tuning fork over the tube, you made the air in the tube vibrate, correct? If I strike the tuning fork and over the top of the tube, is the tuning fork pushing on the air this way, back and forth? So it's sending a sound wave into the tube and coming back up, correct? Because the tube has a closed end on it, the air has to go down and then come back up. Isn't this thing constantly vibrating though? So it's also, as it's sending a wave down and the wave comes back up, do they get each other's way? They do, don't they? When waves get in each other's way, there are places where they cancel each other out and places where they add together, correct? Only happens at certain places. We have to get the waves lined up. When you put water in the bottom and you lifted the tube, what were you changing? You were changing the length. And you were basically finding that sweet spot where the waves wanted to do what? They wanted to add together. So when you hit, you heard the sound the whole time because the tuning fork was also making the sound through the air. But when you got this just right, you were forcing the waves into that point where they added together just right. Did each tuning fork have the same distance that they made the loud sound? No. This is an example of resonance. Resonance is when we are forcing something else to vibrate at the rate something else is. And if we do it just right, if we have the length just right, and we get all of the waves in there adding together, it resonates with a much louder sound than if I don't have that sweet spot.